Hi, thank you for joining us. I'm Pam Hicks with the FAA Commercial Space Transportation, AST, training program. Today we're discussing the High-Fidelity Flight Safety Analysis Advisory Circular, or AC 450-115-1. This is the first of many Part 450 AC workshops, so be on the lookout for more in the coming months. Let's get started with a few administrative notes. We want you to know we're recording and we'll post this session on our YouTube channel. So get your questions in on the Zoom Q&A or using the workshop email, which is astworkshops@faa.gov. Now, it is my pleasure to introduce Dr. Paul Wild. He's Chief Engineer at AST with expertise in launch and reentry, safety evaluations and operations, and explosive safety analysis. Dr. Wild is also a founding fellow and president of the International Association for the Advancement of Space Safety. Without further ado, over to Paul.
Thank you, Pam, for that kind introduction. So it's my pleasure to introduce Dr. Eric Larson, who will be our primary speaker today. Eric is president of the Marigold Rise Corporation. That's a AST support contractor. Eric is absolutely an expert in the subject of flight safety analysis and a primary author of the subject document for today. And Eric is a great friend of mine and a colleague for over 20 years. I also wanted to say how much I appreciate the participation of everybody and all the hard work that goes into developing this workshop. Take it away, Eric.
Thank you, Paul. Much appreciate it. And welcome to everyone. I'm glad that you're here today and hope you find it helpful. This is intended to be, as Pam said, the first in a series of workshops and to help you understand and support the new streamline regulation. So move on to the agenda. The main point of today is to help you better understand the High-Fidelity Flight Safety Analysis Advisory Circular. First, I'm going to give you some background on advisory circulars, what they're for, and how they can help you. And then I'll discuss how this AC fits into the larger picture of doing flight safety analysis for a license. And then the additional ACs, which are in development, will also cover aspects of flight safety analysis. There are other ACs for other parts of the 450 that are also in development, and Charles Hewitt will provide an overview of those at the end of today's workshop. But the bulk of today will be a discussion of this advisory circular, and we'll go through it chapter by chapter. For each chapter, I'll give a brief overview, especially highlighting some key points, and then I'll explain some responses to comments that were formally submitted during the 30-day comment period that occurred after the initial publication of the advisory circular, especially some of the changes that we made to the AC in response that are going to be published soon. And then for each chapter, we'll respond to additional questions that you post today, either through the Zoom Q&A, comments on YouTube, or the workshop's email. And of course, if there's more time at the end, we'll continue to respond to further questions. We want this workshop to help you understand and apply this AC to your operations so that your enterprise can be safe and successful. So let's move on to the background on advisory circulars. You may not be as familiar with ACs. They're widely used across the FAA in the airplane side of the world, but have had less application to commercial space in the past. So the goal for the ACs is to help you and to support your license application process in two ways. The first way is to try to further explain the meaning of the regulatory text by discussing the intent and the goals of the performance-based regulations. This will help you understand what you can do to comply with the reg for your particular situation. Second, the ACs are trying to provide a means of compliance, not the only means, but one means of complying. Thus, if you follow the relevant AC, you will have met that requirement. But other means of compliance are also possible. The FAA encourages industry to develop alternate approaches that provide an equivalent level of safety and meet the regulatory requirements. So let's dive into the topic of flight safety analysis. Next slide, some background on this particular advisory circular. So this one expands and on the Flight Safety Analysis Handbook, which has been around for about 10 years and has been posted on the AST website, but it updates it and expands what's going on. So a complete description, however, of a high fidelity approach to debris risk analysis, which is most of subpart C of part 450, is too broad for just one advisory circular. So you've so far seen 3 advisory circulars that have been published. 2 of them have to do with flight safety analysis, the high consequence event analysis, which is for part 101 or section 101, and then this one, the high fidelity flight safety analysis. But there's actually a number of other ACs that are in development and will be published in the upcoming times. So there's one on normal trajectory analysis corresponding to section 117, one on high fidelity malfunction trajectory analysis covering part or section 119, one specifically on flight abort rule development, how to develop the rules for flight's termination, and that's covering section 108, one on population exposure, which was on section 123, probability of failure for section 131, and one that takes how you take the outputs of a flight safety analysis and develop flight hazard areas. So that covers 133. And then 2 more on other non-debris hazards, one on far field blast overpressure, sometimes called distant focusing overpressure for 137, and then one on toxic release hazards, that's section 139. There's also a plan to have 2 additional advisory circulars that are going to be talking about simpler approaches to accomplishing flight safety analysis. The high fidelity analysis is not the only way to meet the regulation. Recognize that smaller vehicles and that pose less hazard or that can be contained to certain areas, you still need to meet the core risk regulations and the hazard area analysis, but that doesn't require the level of fidelity or detail to demonstrate compliance with those. And so those ACs are also in development, but other approaches that also could be simpler but still meet the requirements are also possible. So let's move on and start looking at the regulation. The next slide. So the first significant chapter or technical chapter is just the terms and definitions. And this is chapter 4 of the advisory circular. Now, one thing to note is that normally the advisory circulars don't redefine or include the definitions that were already in section 401.7 of the regulation. So make sure to look at those definitions because those apply across the entire part 400 regulations, including all of the ACs. But the definitions in the AC itself are scope for terms that are used in this particular AC to try to help understand and explain what's going on. So there's not a lot of definitions in this particular AC, but those terms are reused and used throughout the AC, and the definitions at the front help make the text more clear later on. So one comment regarding definitions was, and this was submitted through the comment process, was what are hazardous debris for jettison cases? And for jettisons, the hazardous debris is the same as for any other type of hazard. And this definition is in part 401.7, and it's any object or substance capable of causing a casualty or loss of functionality to a critical asset. So this includes any type of hazardous debris, whether it's inert or explosive, whether it's an intact vehicle, fragments of a vehicle, any component, whether it's intact or in fragments, the payload, or any planned jettison bodies, anything that can cause a hazard. There are more specific quantitative thresholds in Chapter 11 of this AC, which are the same as are those as are used in RC Range Commanders Council 321, RCC 321. So those provide quantitative values for thresholds that can be used for what's hazardous. But this more general definition accomplishes and incorporates anything that could actually cause a casualty or loss of functionality to a critical asset. So next slide. Second request was for adding a definition of what statistically valid means. And so we are adding to the advisory circular another definition on this, and statistic, and this comes out of text that was in the preamble, but making it also applying it here. So statistically valid analysis is the result of a sound application of mathematics and accounts for uncertainty in any statistical inference due to sample size limits, degree of applicability of data to a particular system, and degree of homogeneity of the data. This particular approach, though, depends on the context of the analysis and is described in this AC and others. So it's basically saying that you need to use mathematically appropriate definitions. This covers the basis to say that, yes, you've got to use developed statistical techniques and mathematics that are appropriate for what is actually being done in this context, and that needs to take into account how you're using the data and how you're running sampling. Okay, let's move on to the next definition. Next slide. So there was a question about foreseeable failure mode, and we recognize this as an important question. What is both foreseeable and a failure mode? So first, to clarify, there's a new definition being added for failure mode, and this is in the context of flight safety analysis. So this is put in this particular AC, and it's defined as a particular category of potentially hazardous events that share significant similarity in system response prior to the consideration of mitigations or any hazard control strategies. So mitigation or hazard control are things like flight abort or a flight hazard analysis that reduces the likelihood. But we want to also make clear that it's not in the definition, but helpful to explain, it's a failure mode is not the outcome of that. The failure mode, it's not the breakup of what happens. Is it a breakup? Is it an intact impact? Does the FTS happen? That is not part of the failure mode. And it's not part of the failure cause. But is instead the collection of the vehicle response, the different trajectory types. So an example of this, loss of thrust, is what we call a failure mode in the context of flight safety analysis. There are multiple causes. You could have a guidance programming error that shuts off thrust early, or you can have an engine failure, but it still results in the same failure mode, which is a loss of thrust. There are also different types of outcomes that could occur after that loss of thrust failure mode occurs, such as an aerodynamic breakup, or it could fall to intact impact. You could have an FTS action, or it could lead to an abort where the vehicle can fly safely to a landing place for a vehicle that has abort capability. Moving on to the next slide. For foreseeable, we added a footnote to try to explain more on what foreseeable is. And this is those that are identifiable through a system safety process, and that includes all relevant failures that have occurred for prior vehicles. So by identifiable, it means that if a solid, rigorous system safety process were followed doing a functional hazard analysis, this is something that you would be able to identify through that process. The things that are not foreseeable, which is just as important to a definition, are things that are, say, not physically possible for the subject vehicle, such as, say, a turbopump failure on a solid rocket motor. There's no turbopump, so you can't have that kind of failure on a solid rocket motor. That is not foreseeable. There's also any unknown unknowns. We recognize that there's always things that could happen that nobody's ever thought of and nobody has never happened occurred. That's obviously not a foreseeable failure mode. Don't need to consider those possibilities. That's trying to give some more context to what we mean by a foreseeable failure mode. There's also legal definitions for foreseeable about what a reasonable person would potentially foresee. So that's where the foreseeable comes from. So now I think if we have any questions, we can move on to the next slide. We say you can use the Q&A chat box in Zoom and chat on YouTube or an email to that email address. And then we can work on answering those. We'll take a moment here to see if there's any questions on the terms and definitions. Okay, I'm not seeing any that have come in, so I think we will move on. Feel free, and we can always come back to these later. But if you do have more questions, then that would be great. Okay, so we are going to now move on to chapters 5 and 6, which provide an overview of how this advisory circular and this section of the rule fits into the larger process of flight safety analysis. So I put together a flow chart here to try to explain how this all fits together, and especially how it fits together with the other advisory circulars that are being developed. So this is phase one of this, which is the using flight safety analysis to develop abort limits or to determine if a flight safety system is not needed, subject to 101C requirements. So on the left side here, you see the core inputs come from the basic vehicle parameters. What is this vehicle? What is the operation trying to do? And from system safety. So you learn about the vehicle, you need to understand this particular vehicle, such as doing a functional hazard analysis, and then what hazard control strategies may be put in place. These feed into two key elements of the analysis. One is the malfunction trajectory analysis. So you learn from the vehicle what kinds of malfunction trajectories are possible and how you're going to model those. You learn from the vehicle description, then how it could break up, and that informs your breakup analysis. There's also, of course, the normal trajectory analysis to figure out what is the plan. And these feed into this part of the process, which is the initial breakup analysis, what happens in the different breakup cases. We'll get back to that, and that's covered in this AC. How these propagate from the time of breakup down to impact with the ground or through the air, potential impact to aircraft, accounting for physics and statistics. And then the potential consequences for impacting people or structures. And then that provides and that also requires the input of the population data in order to determine what the metrics for risk are. Those metrics that come out of the debris consequence analysis, especially the CEC, inform whether or not you need a flight safety system per 101, and if you do, or if you have a flight safety system, then in the 108 section, and then that AC, we'll talk about how to develop abort rules and then how to apply those to your malfunction trajectories to determine the states where breakup will occur. So now let's go on to phase two on the next slide. So we've developed our abort rules and we've applied those to malfunction trajectories. We have our normal trajectory, we have our breakup analysis, and we have the population data from the previous phase. And now we need to apply the dispersion to those the breakups that resulted from applying your abort scenarios, and how those now affect and reduce the hazard from the debris on the ground. Those then get combined with the population data. And now here's where your probability of failure comes in to evaluate the actual risk measures. And those risk measures need to get measured for debris, which is covered by this AC, and then for the far field overpressure, which is going to be covered in the AC 137, and the toxic analysis covered in 139. The debris, overpressure, far field overpressure, and toxic all then come together to determine whether the mission meets the core risk requirements in 101 for EC, and then also what flight hazard areas need to be developed. Those are going to be aircraft, ship, and land hazard areas. And then those will feed into how those hazard areas need to be controlled for the operation. So we will now move on to questions on this section. Oh, wait, sorry, we have some comments. Sorry about that. So first, there was a comment in general on 1 second intervals for trajectories is excessive, excessively frequent for some parts of flight. And wanted to clarify that this is only for normal trajectory data, and it's actually required in the regulation 450-117. It was also a carryover from the old 417. And for normal trajectory data, we definitely think that 1 hertz or higher frequency is reasonable for that. Malfunction trajectories don't have that explicit requirement necessarily. And this will be more covered in the other ACs. There's also 3 other comments that will actually be answered in future ACs. There'll be the trajectory file formats, what will AST expect? And that will be covered more in 117 and 119 ACs. And just to point out, there will be no particular format specified, but there will be clear expectations for what needs to be included in those. But we want to give flexibility to operators to be able to develop that, and AST has tools to be able to ingest different formats subject to certain conditions. There's also a number of questions on limits of useful mission and the flight mission limits, and those will both be covered in those two trajectory ACs, the normal flight trajectory and the malfunction flight trajectory. So let's move on to the next slide. And now we have some questions. So one question was, when will the FAA release those other advisory circulars? And we are going to cover that somewhat today at the end of today's workshop. And then also there will be future announcements when the schedule can be further updated. And then another question is, how can operators comply with Part 450 until these additional advisory circulars are released? And we encourage operators to propose their own means of compliance or use existing standards that are already out there. So those are two ways to meet those requirements for now. Looking ahead. So there's a question on whether the FAA will maintain a database of flight history for operators to use for probability of failure analysis. And the answer to this is no, the operator should use the best available data. There are public sources out there which contain quite a bit of launch history. And so there is some publicly available data on this, and there'll be more guidance that will be provided in the advisory circular on 131 probability of failure. Okay, let's move on to the next slide, moving on to chapter 7. So this is on the different hazardous scenarios that can result. And it's important that there are different scenarios that result in different kinds of debris. Oftentimes the most important in terms of consequence is the intact impact scenario. Upon intact impact, it can be important because you can have an explosion there, which generates a blast wave, and also can then shed or cause additional debris to come out of the that explosion. There can be a toxic release, this can be particularly important if you have highly toxic materials, and that toxic cloud then can cause hazards, cause casualties to people in the vicinity of that impact. Another important case is a gliding impact for a winged vehicle. If it comes down in the wrong location at high speed at a shallow angle, this can cause a very large area where people can be injured. The mid-air explosion case, of course, this can lead to a lot of debris. What's particularly interesting here is also the small debris that's important for protecting aircraft, because the aircraft are, of course, more sensitive to small debris because of the speed of the aircraft. So that's an important consideration there. For flight termination action, it's important to model what the outcome is. There's a lot of different kinds of termination results. You can have a destruct action, which may be similar to an explosion, or a thrust termination event with venting or without venting of propellants. And also, one outcome can be abort flight, if a vehicle can then continue flying under an abort condition. And this will be covered in the malfunction trajectory analysis. For aerodynamic breakup, we have observed from some events hundreds to even thousands of fragments resulting from an aerodynamic breakup during descent, or a vehicle powered and once it exceeds its structural limits. And then for vehicles re-entering from high altitudes, then you can also have to deal with aerothermal heating, and then this can cause the breakup of the vehicle. Some vehicles are, of course, designed to break up and melt and produce very little fragmentation, but a vehicle that's actually designed to survive can produce a lot of debris on the ground. The Columbia, of course, is the classic example of that, which generated far more fragments than had been anticipated before that accident occurs. I'll also say that this is an area that AST is looking at expanding and providing further guidance on development of debris lists. There's several pages on it in this advisory circular, but this may actually become a whole separate advisory circular that goes into more detail about how to develop debris data. So moving on to the next slide. Okay, so there was a question about, can we provide, since part of the requirement is to validate data based on historical experience, and are there expectations that's not generally publicly available for what debris has resulted? So since that comment, we performed an additional analysis of historical debris lists, and we'll be adding a new paragraph to the advisory circular, paragraph 8.8, which includes guidelines and includes equations that give how many fragments to expect that are greater than 300 grams, and the total basic casualty area. And it's a function of the weight of the vehicle. There's two scenarios for which there was enough data to develop these. One for a midair explosive breakup, and then the second is for an aerothermal breakup of vehicles designed to re-enter from orbit. So there is, however, insufficient history at this point to generalize for other scenarios, and sometimes it's just simply too vehicle specific to be able to do that. But at least to try to help applicants in evaluating their debris list and understanding whether what they're coming up with is consistent with what has been in history, these guidelines will be added to this AC before on its next publication. Okay, that's the next slide. Okay, there's a couple of comments on what was section 7.1.4, determining population and geographic areas affected by hazardous debris. So first, the title of that paragraph is misleading because it doesn't actually talk about the areas that are affected, but what characterization is needed of the debris in order to do consequences. So that's going to be changed. Also, there was questions for references for population data, and yes, we understand this need, and that is part of what is being intended for the population advisory circular that will be coming out. There's also a question on aviation traffic density data, if that could be provided. And that is actually not necessary. There's air traffic densities are not applicable to complying with the regulation. Hazard areas are the methods that are used to control aircraft risk, not dependent on the density of aircraft in the region. So because aircraft risk is measured only on an individual basis, not a collective. So there's no reason to need any aviation traffic density data to comply with the regs. So let's move on to the next slide. Okay, so some other questions. Okay, are there recommended degree of freedom models such as 3DOF or 6DOF for analysis? 6DOF is required for the normal trajectory analysis, and that's required in 117, and some specifications of that will come in the normal trajectory advisory circular. But yes, for malfunction trajectories, lower level fidelity is sometimes available, 3, 4, or 5 DOF models, and that will be covered in the malfunction trajectory analysis advisory circular. Oh, so there's a question of why was 300 grams chosen rather than a different mass, say 450 grams or 3 pounds. And the reason for that is because the 300 gram pieces, that's the threshold for aircraft vulnerability models between the smaller pieces, which have a vulnerability area less than the entire size of the aircraft, and how much can potentially cause hazard to the entire aircraft. There's a lot more uncertainty below 300 grams and less clarity as to what is actually true there. There's enough experience and data to come up with the larger values, but the 300 grams was specifically because that's an inflection point in the vulnerability models for aircraft.
Hey, Eric, I'd like to add to that answer. So the FAA has done some testing where we looked at impacts on aircraft, and we saw that at the 300 gram level, it's possible to defeat primary structure. And so that's a very key threshold for aircraft vulnerability that's grounded in some test data. Eric, you're doing a great job. There were some other questions about malfunction trajectories and doing those for piloted vehicles as well.
Right. So yeah. So do you need to do a malfunction trajectory analysis for pilot vehicles? And yes, in the past, operators of pilot vehicles have used flight simulators to model malfunction trajectory analysis. And the FAA is also working to publish an advisory circular specifically on hybrid operations as well. Okay, let's, I think, keep on schedule. Let's move on to the next slide. Okay, so this chapter discusses more the quantitative characterization of debris. The previous chapter was about what scenarios need to be covered and the important factors. This one goes through the different quantitative values that need to be developed. So there's basically four properties and then a particular area on statistics. So the first that needs to be quantified are the initial conditions, which is what is the position and velocity distribution for your debris at breakup. And this is both a function of the vehicle uncertainty, as well as the dynamics of the breakup event itself. And then you need to characterize the aerodynamic properties in order to be able to propagate the debris from the breakup point down to where it impacts. Need material properties when you're dealing with aerothermal demise. That is not always needed for cases that don't change properties during propagation. So that material properties can also be important, say, for solid propellants that may still be burning. Then the properties that are required to characterize the hazard. So what is the mass, the area upon impact, which affects the calculation of consequences to people in buildings and structures, and also to critical assets. So those are the four areas that need to be quantified in order to do a high fidelity flight safety analysis. There's also guidelines for how to group debris together, because grouping debris can help smooth out some statistics to not just have individual discrete debris fragments. And it also then ends up reducing computation requirements when you do that. But you can't overgroup debris, make too large groups, or you can lose important information. We're also, the FAA is interested in more empirical data regarding any debris characterization, both breakup events and intact events. This is certainly an area of research that could be improved, and AST has been trying to gather data from past events and accidents and do tests to try to understand this whole, what happens when a vehicle breaks up or impacts better. Okay, let's move on to the next slide. Okay, so there were no comments previously submitted in the formal comment period. So there's a question with respect to relevant prior failures. Much information is not publicly available. So will AST provide data on historical failure modes, failure databases, or an AC appendix to ensure the operator meets system safety assessments and those meet requirements? So as we said, we're looking at expanding the section on expanding this section of the AC on debris, perhaps into its own AC, and providing more information on debris and how to develop it and what we know would be helpful, but that is still being contemplated at this point. Another question was, does the FAA have a specified format for debris data? And the answer here, no, the FAA is not going to specify a particular format for debris data. It will be in the AC. I think it lists what parameters are expected, but a particular format, generally debris data is submitted in a spreadsheet format. It's tabular data, and then the FAA can work to translate that, and we'll work with each applicant to make sure that what they have provided is sufficient for the analysis. Okay, so there's also Okay, so there's a question of, is a single breakup analysis of the worst case cause of vehicle breakup acceptable, or are multiple analyses needed? And so the answer for a high fidelity analysis, no. The debris analysis needs to cover the different types of breakup modes. And it's often hard to determine what is the worst case event, because it also depends on where your population is located and what assets you're concerned about. And sometimes worst case may be intact impact for ground risk, and it's usually a breakup, and it's a breakup case for an aircraft hazard area. So those different scenarios need to be considered rather than just a single breakup list. Okay, let's move on to the next slide, to chapter 9. Okay, so chapter 9 discusses the propagation, which is the physics and statistics that take the debris from the point of breakup down to where it impacts either aircraft or structures or ships on the ground. So there's the key aspects here are atmospheric data. The environment is, of course, very important, density and wind being the most important for debris. The failure and the planned event state vectors, that's the initiation points. The statistical trajectories, so what do you need to be what is sufficient to be able to characterize the statistics of debris fall? And how do you simulate those trajectories? What are the mathematics that go into the 3 degree of freedom, typically model of tumbling debris? There's also some particular special topics that don't apply to in every situation, but in some, such as residual thrust, there's still, when you have an event, a failure or breakup, partial breakup, you may still have residual thrust in some motors. Some vehicles will still have directed lift, that a random lift model is not appropriate. How do you handle that? There can be progressive breakup. Breakups are not instantaneous, except sometimes explosions are pretty instantaneous, but certainly structural failures can take some time, and aerothermal breakup certainly happens over a extended period of time. And then also aerothermal demise, how much melts and then doesn't actually reach the ground, but melts and then vaporizes in the air. There's one particular aspect that we wanted to bring up in terms of atmospheric data, and that is that wind in the vicinity of, or two things, in the vicinity of the operation, either the launch or the landing site, you should look at wind as a variability. You'll know at the time the operation starts much better what the wind conditions will be. The forecast 24 hours, 48 hours are quite good. So we need to count that wind as if we need to know at the time of the launch, you will know what that wind is going to be. So you need to plan for that. You can't say, oh, well, we're not going to be sure what it's going to be like at the launch time. Instead, you need to plan, okay, we will know. So the uncertainty at launch time will be small, but some sort of sensitivity study or a launch day countdown analysis will be done with the right winds to account for that, because the uncertainty gets smaller, which can have increase the probability of impact for areas that are directly under the trajectory, especially, which affects ships and aircraft hazard areas. We've also seen that for shallow angle reentries, the high altitude density of the atmosphere is quite important. And so that needs to be modeled. You can't just stop the atmosphere at, say, 100 kilometers if you're coming in a shallow angle, or it will mispredict where the debris will end up. Okay, so then moving on to the next slide. Okay, so there were no other questions on this section. There was one that was asked through the comment or through the chat. Will AST require statistical wind databases by altitude be used versus average mean winds over a given time period, such as a year or 6 months? I would assume that statistical winds in a Monte Carlo simulation is preferred, but is computationally intensive. So, so this is definitely a complicated question to work out. So worst case winds will be needed to be analyzed in order to assess the extent of the hazard areas that you're going to be using. Typically, if you notice, the requirement is not that you analyze all wind conditions necessarily in ahead of launch. There's two cases discussed in 135. One approach is to do an availability study and to demonstrate that your hazard areas and your risks your hazard areas encompass all of those that could be produced by any given wind on launch day, and that your EC is acceptable. Or you can do a countdown analysis and demonstrate then that your risks are acceptable with the countdown. So it's not necessarily that you need to use a large set of statistical winds to do that. There's well ahead of time. It's really looking at worst case or doing a launch day countdown to ensure that your risks are still acceptable and your hazard area is acceptable at the time of the operation. Paul, did you want to add something?
I did. Thanks, Eric. So that's a really great question. The winds can indeed have a significant influence on the debris, and it's can be quite complicated. But the point that I wanted to make is that statistical winds and their perturbations, the most difficult aspect is getting the inter-altitude correlations correct. So you typically need covariance matrix based on past data to understand how those inter-altitude correlations can be modeled reasonably. And our past experience suggests that by far the best way to do an analysis involving a large set of winds is not to start with a statistical description, but instead to start with a library of actual sampled conditions. And those types of things are available these days through various weather services, including, of course, NOAA and the Air Force.
Okay, so let's move on to the next chapter, chapter 10. So chapter 10 talks about probability distributions. Since, of course, failure events have a lot of uncertainty into actually what is going to happen when a failure or breakup occurs. So this chapter defines what impact probability is and discusses three different ways of developing distributions of impacting debris. One is to use a Gaussian approach, bivariate or trivariate normal distribution. But for some cases, that doesn't characterize the debris distribution very well or sufficiently. And then a skewed distribution is a higher order one where you're still aggregating all the debris from a certain fragment group into a single distribution, but it's a skewed approach. And there's some discussion of the mathematics and approaches for doing that. Or in other cases where you really don't have a good distribution at all.
Andrew?
Or Paul, did you want to say something?
No, sorry, Eric.
Okay, so then, or you also, in some cases, you actually want to use a histogram where your distribution is better, histogram type approach smoothed with something like a kernel density estimation. This is particularly helpful, say, for intact impacts where you don't have as much uncertainty in the propagation, but only you tend to model it more discretely. And so then you need to aggregate a set of impacts into something that's smoother, that may not represent something that's easily identifiable as a Gaussian skewed or some other kind of distribution like that. And then, of course, for aircraft, you need 3D or 4D distributions to be able to assess the risk to aircraft at altitude. Okay, let's move on to the next slide. Okay, so that covers a review of that, but there were also no comments specifically on chapter 10. And I don't yet see them on the from the chat. Okay, well then why don't we let's move on to the next slide, to chapter 11. About consequence models. Of course, consequences, there's a lot of work that's been done here. So first, it defines what the consequence measures are. So what is a casualty, which is based on the AIS level 3. What is casualty area, basic casualty area, effective casualty area? What do those mean and how are they used in the analysis? And then what is probability of casualties, some events, explosions, toxic releases, and some others are actually it's a probability as a function of distance from the impact point, say 100% probability within a few feet, but then as you get to hundreds or thousands of feet away from the impact, that probability goes down. And how do you integrate those? There's two major categories of looking at consequence, whether people are unsheltered, outdoors in the open, and so the effects, the hazards are directly affecting people, or if people are inside a building or a ship or an aircraft, how does that structure affect the casualty area that's producing? Obviously, for small debris, having a roof over your head will provide more protection, but if it's a larger piece of debris, it can start to bring down the structure itself and cause a larger hazard area than there would have been just from the original debris. The AC also discusses looking at the consequence for different types of debris, whether it's inert debris, and there's curves in there giving the casualty area as a function of ballistic coefficient and weight and area. The consequences for different size explosions, some about the consequences from toxic releases, from burning propellant. If you ignite either the fireball from a liquid propellant or igniting a fire in a building, say from a solid propellant, burning piece of solid propellant impacts the structure. And then some discussion of intact impacts and how to deal with those cases where certainly, especially a shallow angle impact produces some much larger casualty areas and hazard areas than when it breaks up or comes in more steeply. And let's move on to the next slide. Okay, so there was a comment on paragraph 11.8 talking about the consequences to people and aircraft. And it was requesting clarification that the analysis does not apply to published or controlled flight hazard volumes, which are assumed to be clear of aircraft during the effective time of the hazard. And while it is true that aircraft are generally assumed to be clear, provided that the notices have gone out properly, monitoring is still done, but you still, even if that were true, you still need to model the consequences to people in aircraft and the debris consequences on aircraft in order to determine the size of the airspace that needs to be cleared. So that's an input into the analysis, which then is used to determine those aircraft hazard areas. So that those consequence models, part of the work that's been done to develop better consequence models for people in aircraft has resulted in smaller hazard areas needing to be published for aircraft because then you can ignore, or the debris, the very small debris no longer causes a hazard or no longer can cause a casualty because the aircraft structure will protect the people inside. So that is relevant to hazard area determination. And moving on to the next slide. Okay, so again, there were no particular comments on this from the original feedback. There was one question asked today, where can an operator find more information on vulnerability models? And there is more information in the RCC 32120 supplement. And as you might have noticed, that's now been released publicly. The previous supplement was not, but this one now is available publicly and can be retrieved over the internet. So that has more information on vulnerability models and consequence than is in the AC. And there's no other questions. So let's move on to chapter 12, which is discussing the consequences of risk. So of course, this is where first we need to define more mathematically what the actual risk metrics are. So it defines CEC, and that's actually further discussed in the high consequence AC as well. And basically, I got a couple of simple equations there. Basically, the CEC is specific for a failure mode in a certain time interval. And then EC is just integrating all of the CECs when they're multiplied by the probability of that mode at that time. So that's how CEC and EC are related. Another important metric is the individual probability of casualty, because for individual risk, that is also one of the metrics in 101 to limit the probability of casualty to any particular individual from an event. And then also discussing probability of impact, which is important for measuring the consequences to structures and critical assets. And just a reminder that impact probability doesn't stand on its own. It is always relevant to what is the probability of impact on an area or some defined size of object and what fragment characteristic that applies to. Is it greater than 11 foot-pounds, greater than 1,000 foot-pounds of impact kinetic energy? The second important piece of this that I would really encourage you to look at closely is the comparison of doing the availability study, which is, I talked about a little bit before in responding to the question about using winds. And you may want to do this for your mission assurance as well, is to look ahead and say, what are the range of wind conditions? What are the range of vehicle variability that will be, that this mission will meet the risk requirements? So there's variability in terms of, say, when in a launch window, a mission might actually operate. Sometimes that significantly affects the trajectory. For a mobile launch platform, where in the where in the drop region or where in the launch region that is actually going to occur needs to be looked at. And then also the approach to do it during the operation countdown. So in the last, say, 24, 48 hours before the operation actually commences is the alternate way to be able to establish the safety of the mission to meet the risk requirements and demonstrate the hazard areas are adequate. So we'll move on to the next slide. Oh, so there were no comments here. I haven't received any comments in the chat either. I think most of this section, except perhaps that looking at the two options for the availability or the countdown is pretty standard and conventional. But that part, I think I would definitely recommend looking at and understanding how you're going to approach that for your analysis. I think one thing I will add to this is that it's also important to that is that as part of your application submission here, it is demonstrating that your process that you're using to do that risk calculation is adequate to demonstrate compliance in the launch countdown, that you're actually meeting the risk requirements. Really, the important thing about all of these sections of subpart C is demonstrating that the process that you as the applicant will be using during the countdown is adequate to meet those safety requirements. The actual products that are submitted for any particular mission are actually covered in section 213, the pre-flight data package that includes some products of the safety analysis, but that's particular for each particular operation. Paul?
Hey, Eric, one thing I think is worth adding is that obviously one of the most important products from the flight safety analysis is to identify the launch commit criteria. I think some of the questions about the winds were aiming at that, but clearly, there will be wind constraints that you wouldn't want to fly your vehicle through, and also there could be wind constraints that, given the size of your hazard area around the launch point, you can't keep that hazard area would not be valid if the winds exceeded the launch commit criteria. Thanks.
Okay, so let's move on to chapter 13. So this chapter discusses the hazard areas, and there's three types. There's protecting people on land. What is your keep out area on land for where you're exceeding the 10 to the minus 6 probability of casualty. There's then over water, notices to mariners, and for airspace, notices to airmen and or temporary flight restrictions and other communications to air traffic control to keep a region free of aircraft. There's both warning areas and exclusion areas. So a warning area means that it is possible that you may say have ships inside of an area which you've warned them to keep out of, but then a launch evaluation can be done on risk-based and to determine if that particular ship is actually causing any exceedance of criteria. But there's also exclusion areas where you need to say no ships or no aircrafts can be in this area at the time of launch. So there's some flexibility there. Warning areas are helpful in terms of mitigating risks that you may still be acceptable, and exclusion are those areas that are necessary in order to meet the risk criteria. It also discusses the calculation to some degree of how you go from your impact distributions typically to grids that evaluate the risk criteria as a function of location. And then the grids are turned into contours, which then are bounded by usually simpler boxes that are actually issued as the warning or exclusion areas. And again, this is an area where the FAA is looking at expanding the guidance and developing additional information about how to create these hazard areas and further discussion of how to use warning and exclusion areas to meet that. Okay, let's move on to the next slide. Okay, so there's a comment that to clarify that aircraft hazard analysis within U.S. airspace may be performed by the FAA. And the answer to this is that AST does not plan to perform the aircraft hazard area analysis in general. This is an operator function per 133. It's part of the flight safety analysis products that come out of that. Of course, operators do often contract with a federal site operator or federal range to do this analysis for them. But in general, AST may do some analysis to validate the results, but in general doesn't perform this analysis or duplicate applicant analyses to come up with this. Okay, next slide. Okay, so again, there were no formal comments, but we have received some questions regarding this in the chat. So one was, why has the containment requirement for normal flight events, say jettisons, changed from 3 sigma to 97% probability of containment? And the key thing here is that 3 sigma is not sensitive to the number of fragments that actually result. From the 3 sigma area doesn't include these, and 97% confidence of containment does account for those cases better where a jettison failure or jettison body breaks up during descent, and that all of those fragments need to be contained. So this has already been how the federal ranges through RCC have been operating. So this is now more consistent with the federal range approach. There's a question, will there be additional coordination in the future to exclude recover areas in order to avoid problems with mariners interfering with recovery operations, such as the Coast Guard? So this is an operational question. In some ways, if the recovery needs to occur, the FAA is concerned with safety, but there's a requirement in Section 147 that requires agreements with the Coast Guard. So that is part of the requirement, is to work with that. So those procedures need to be established prior to issuance of a notice to mariners, prior to a launch or reentry, and any other measures related to that to protect public health and safety. So that is a requirement that those be coordinated with the Coast Guard for safety issues. You, as an applicant, may have, of course, additional operational requirements that aren't necessarily safety that do need to get coordinated with the Coast Guard as well. There was also what is a good resource or reference for developing models for doing this analysis? So the reference 1 of the AC does provide quite a bit of information. That's the book, The Safety Design for Space Operations. So I would look at that one as well for additional information about how to more details of the mathematics of doing many aspects of this analysis. Okay, let's move on to the next slide, talking about application requirements. Okay, so notice that this does somewhat overlap with what's actually covered as other sections as well. So this section will probably be revised to be more specific to the parts of the regulation that this AC particularly covers, which is debris list development, the propagation methodology. They'll have a consequence analysis and how that relates to what debris is being modeled, and risk results that you get out of it. So those are the things that are specific to this advisory circular that are going to be covered here. So the application requirements, again, a key thing here is that as part of the application, it's a process that we're really saying, yeah, you're putting forth, here's the process that we're going to use, along with sufficient examples to demonstrate that process. The FAA is evaluating then your process for ensuring that the risk criteria are met, and that includes the hazard areas. So the application requirements are to describe the process that is going to be used for all operations that are covered by this license, and the representative results for one operation. Not the results for every operation at the time the license is submitted, or for the results that would cover all of those. Instead, it's here is the process which is sufficient, and your assertion that you will then follow that process for subsequent operations. But the per operation requirements, that I mentioned a little bit before, are specified actually in section 213, the pre-flight reporting section. So that's what needs to be submitted to the FAA for each individual operation. Part of this approach is to try to streamline, to make it clear that, part of the streamlining is that a license can cover many different operations, and not every operation goes through the entire licensing process, but the process is what is part of the license application. Okay, so then next slide. Okay, so again, there were no comments here that were submitted before, but there have been some that have been submitted through the chat. So one of the questions was sort of related to how many, it's more related to another AC, but how many trajectories are expected to be needed to characterize a type of malfunction? So there's not going to be a specific number. I mean, it depends a lot on the malfunction and where malfunction occurs, where those hazards are. But there's a performance standard, which is in 119B, which is the analysis for each type of malfunction must have sufficient temporal and spatial resolution to establish flight safety limits, if any, and the individual risk contours that are smooth and continuous. There will be additional guidance on this topic also in the advisory circular that's in development for malfunction trajectory analysis. There's also a question, does the FAA intend to accept federal launch and reentry site analysis without additional data being provided? And of course, the FAA has worked with federal ranges to develop the approaches and the methods. So the FAA will accept the analysis of a federal site as long as the FAA has reviewed and accepted their processes for that site, and to the extent that those analyses meet the FAA's requirements. There will, of course, be some additional data required to be submitted, such as so the FAA can do the maximum probable loss determination, and there is specific data that's required per operation per 213. So, but the approaches and the methodologies that are used by federal ranges, if they've been determined to be satisfied, of course, that would be sufficient. Also, are there commercial operators that can help launch operators meet all these requirements? And of course, yes, there are various contractors available to perform launch and reentry safety analyses, including doing this high fidelity, including, say, doing the sources for weather data, helping to coordinate hazard areas. So there are contractors out there that can support this kind of operation. And let's see, will there be additional core? Okay, I think I already talked about the Coast Guard to some degree. Okay, so I think that covers going through chapter by chapter of the AC. So now I think we can move on to the next slide. Okay, well, that's getting on the process. So there are a few other general questions that didn't get answered before, and we have a little bit more time here for these kinds of questions. So will the FAA make available software tools to model explosive breakups? And no, the FAA does not plan to make available those software tools. As we mentioned, there are contractors and that are out there that have provided those, and also the FAA is open to other means of compliance to do that, that analysis. Paul, is there one that you want to pick up here?
No, you're doing a great job. I'm just here for moral support.
Thanks. Okay. Just reading over the questions that I've seen here.
So there's a question, Eric, about publicly available data to validate the debris data. And I know that we've been doing some work on that. So you can go ahead and tell them what to expect is coming in the revised.
Right. So yeah. So as I mentioned, we're going to provide some guidelines for the debris data in terms of the number of fragments and the basic casualty area for explosive tank breakups, liquid fuel tank breakups, and for aerothermal reentry. And hopefully, as can continue that process to provide additional data, both on the parameters that are going to be outcome from that, as well as for different types of breakup scenarios. Also, there's more questions, not just the breakup, but also failure scenarios. So there's a lot of data available in terms of success and failure. There's websites. One example that's out there that's freely available data is Gunter's space page. It contains a huge amount of information on successes and failures of past flights. So, and the FAA will also work with applicants on through the pre-application process to provide additional data as necessary. So that is something to bring up. But overall, there are other sites out there that have a lot of information on the general success and failure, and even some specifics on failures, but that's also something to bring up as part of the pre-application process.
So
there's
Eric,
a question. Yeah, go ahead.
There's a question about if the recommended breakup debris data guidance will be launcher size dependent, and absolutely, the graphs will be as a function of the dry mass of the vehicle for different vehicle types.
Yeah, there's a question, is this briefing going to be recorded and available on the website? And yes, all of the Part 450 workshops that were done before and all the advisory circular, these workshops will be available on faa.gov/space, and then go down the streamlining regulation process on the left. So the video is available for the 3-day workshop that was held in November, and this one will also be posted there.
I think that's about it for our questions. We're still open to questions. How are we doing on time? I think we're pretty good on
about
time.
5 more minutes for questions, I think, if we want. So we got 20 minutes total, and Charles is going to cover some
Okay.
things.
I'm looking for additional questions. Okay, so there's this question, while there are contractors support flight safety analysis, according to AST, only one has a safety approval. is AST reviewing other contractor processes, methodologies to enable other commercial services or operators without impacting the licensing schedule. Of course, that's not under our control. The contractors have to apply for a safety approval. You know, the companies that are out there are quite well known and do a great job. And often they have their specialties in terms of vehicle types that they're used to working for. But we have no additional applications for safety approvals in the pipeline at this time.
Okay, so there's another question that if we have analysis showing that high altitude, high velocity debris will demise, can that analysis be used to reduce the expected casualty area? And given that demise modeling is more of an art than a science, are there conservative guidelines for performing this analysis? And so the answer is yes, demise can be modeled, and that's, you know, there's some discussion, a little bit of that in the advisory circular. There is certainly some uncertainty on that as to what outcome you get. NASA's, of course, done some definite work on this topic. So I don't think that at this point that you know, AST is going to be ready to publish guidelines, particularly on that topic. The total casualty area, the basic casualty area that is shown on the that we're working on adding to the advisory circular in terms of those guidelines is intended to be for ground impact guidelines. It's actually especially difficult to understand how much debris is hazardous to aircraft from an aerothermal reentry. The small debris is not well known, and it's especially not well known how much of it will actually demise. And even, you know, the data, I worked on the data set from Columbia and trying to estimate how much of that was hazardous to aircraft. There's easily an order of magnitude uncertainty as to how much reached aircraft altitudes, perhaps more.
Yeah, so on that, I would just add, you did some great work on that, and I remember working in Columbia with you very fondly. So the guidelines that will be coming up are based on data from real events, such as Columbia. So there is some demise that has been, you know, built in to that empirical data. Yeah, doing the analysis for, you know, aerothermal heating and the extent that would demise fragments is complicated. There are some tools out there. Eric mentioned NASA has a DAS tool that does perform a conservative analysis. And so there are some things that can be leveraged. There's some data as well in the reference number 1 in this advisory circular, the chapter on reentry, that also could be used to help you know, calibrate or verify a particular model for demise. But you know, for the longest time, probably up through, I think the first, the Delta IV was the first launch where, you know, for the upper stage, some potential demise of debris following failures, you know, late in flight as the vehicle is approaching orbital velocity was accounted for. And, you know, of course, the conservative analysis is simply ignore demise. In cases where, you know, that presents a real limit to launch availability or the ability to launch, we have, you know, reviewed and approved analyses that account for demise, such as the Delta IV upper stage. And so this is an area where we'd be looking really for a unique means of compliance by the operator, or using a tool such as DAS, or the equations that it's based on. So that's about the best we can do at this time. Yeah, I'm not seeing any other questions. I'm not surprised. Thermal demise kind of is the final question.
Okay, so I think now we'll hand it over to Charles, I think, to review the upcoming, the overall ACs and process.
Thanks, Eric.
Yep, thank you, Eric. Great job in going through all the parts of the AC. And I'd just like to take some time now to go over what our advisory circular process is and try to give you an idea of when you can expect some of the advisory circulars. So once we develop an advisory circular, it goes through a series of reviews, including internal management, and we also go through the Common Standards Working Group, which is made up of DOD, NASA, Commerce, all our government partners. So and we have a lot of people that are very, very knowledgeable in a lot of these subjects, from the ranges that go through the ACs to make sure that they're technically sound and make sense. And after that review, then it goes through a legal review, and then it goes over to the Office of the Secretary of Transportation, and then on to the Office of Management and Budget. And that is only if they are deemed significant. And right now, the only thing that would make them significant is if there's some kind of, if one of our government partners has an issue with the AC. So then our intent is to publish the ACs with, and then have a 30-day comment period, which you would be able to provide us with comments. And during this comment period, we intend also to hold one of these workshops to give you the opportunity to talk to us and ask questions and interact, because we want to be able to have the best AC that we can, that meets your needs. We're not doing this for our amusement. We're doing this to help you be able to have a successful application. And then after we receive your comments, we'll address them and publish a final version. And sometimes we won't be able to take all of your comments, and because different companies have different interests, and sometimes they are divergent, so we can't make everybody happy. We will try to address as many of the comments as we can. And I would also like to note that once the ACs are published as final, they're never truly final, because ACs are always open for public comment. So they will continue to be open for public comment, and we'll be able to update them. If we get significant comments that require changes, then we can update the ACs at that time. Next slide. So now I'll go over all the plan for publishing the ACs. So we already published 3 with the rule, which were the High-Fidelity flight safety analysis that we went over today. And we also published the high consequence event protection and the computing systems and software. Our plan is to publish 3 other ACs that will be coming out at the same time as the rule becomes effective. And those will be the flight abort rule, the hazard control strategy determination, and safety critical ACs. Next slide. And then after that, there's a transition period that is actually 90 days after the there's a typo there. So it should be at 90 days after the rule is published. So that would be sometime in June timeframe based on the publication date. So those will be the mishap reporting, response and investigation AC, the system safety program AC, flight hazard analysis AC, normal trajectory analysis, control of hazard areas, and pre-application consultation AC. Next slide. And then finally, there'll be a series of ACs that we plan to publish by the end of the fiscal year. Sometime in September timeframe. And those are the distance focus overpressure risk analysis, the toxic hazard analysis, tracking, collision avoidance, ground safety, mission data loads, flight safety analysis, hybrid launch systems, which won't be really a means of compliance, but rather it will be a guide on how to deal with hybrid launch systems. And finally, high fidelity malfunction trajectory analysis. Next slide. We also have physical containment flight safety analysis. Those are for operations where you don't really have enough energy to be able to go outside of your hazard area. And also probability of failure, population exposure, and medium fidelity flight safety analysis. And on the mission data loads AC, there's also concurrently being developed a standard by one of our government partners. So that will be another means of compliance that you'll be able to use. And we might just refer to that a standard in the AC, or do away with the AC since there's already a standard there. But as of now, we're planning to have that AC published. And that's all I have. Is there any questions on the publication of ACs? Yeah, and our ACs will be published on our website there. It's on the chat, the address. Yeah, ACs are normally not published on the Federal Register like rules are. All right, so seeing no questions, I'll turn it over back to Pam. Thanks a lot.
Thank you, Charles. And thank you, Eric and Paul, for sharing your expertise with us today. Thank you, Charles Hewitt, for providing the AC development update. Charles is a lead aerospace engineer in our Policy and Innovation Division. If anyone has any questions or any feedback at all, please email us at the email address astworkshops@faa.gov. And look for our next workshop announcement. We're projecting late March, early April for the other 2 ACs that were published with Part 450. And just a note to the industry stakeholders that we will be holding regular Zoom meetings as these ACs, all these under development now, are put out for comment. We're going to hold some meetings where we're really discussing those in depth to get them out in a better form. So that's it for today. Our special thanks for our production team. Thank you again for joining us today, and see you next time.